In this video, we will discuss hydrogen-like atoms. Hydrogen-like atoms have one electron around the nucleus, and in the nucleus there are Z number of protons, so atomic number is Z. So we have a system in which we have two particles, one electron and another nucleus, and we can write the potential energy, which is of course a central potential. And what we will do in this rather long video, that we will find the eigenenergies and eigenfunctions from the solution of Schrodinger equation, and we will see that those eigenfunctions are also simultaneous eigenfunctions of L square and Lz operators, as we have seen before. So hydrogen-like atom is actually a very important model, because it not only tells us the properties of hydrogen atom, but also provides a very good model to study multi-electron atoms and also molecules up to a large extent. Because we cannot solve Schrodinger equation exactly for multi-electron atoms, for example helium, lithium and so on, but we can use the solutions of hydrogen-like atoms to build the solutions of multi-electron atoms and molecules. So that's why hydrogen atom or hydrogen-like atoms solutions are extremely important, and they provide us a language to talk about multi-electron atoms and more complicated molecules and other small structures. So let's begin with this structure. The potential for these two particles, we can easily write it, that is given by Coulomb law. It's 1 over 4 pi epsilon naught. Ze is charge on the nucleus, E is charge on an electron, and R is the distance between the two. And since we are going to be using it in several calculations, let me define this new parameter Z prime such that Z prime is Z over 4 pi epsilon naught. So that we don't have to keep writing all of this again and again, we just can write this. And our goal in this lecture is to find the eigenstates psi, which are the eigenfunctions of the Hamiltonian operator, and their eigenvalues, that is the energies, in position space. So we are going to be finding these states in position space, and along the way we will determine the energies of those states. Okay, so to begin this, we need to write Hamiltonian operator in the position space, which is the sum of kinetic and potential energy. So kinetic energy term is momentum square over 2 mu plus the potential energy, where this mu is the reduced mass. If the m is mass of electron and capital M is mass of nucleus, then we have already seen that we can write the relative part of the Hamiltonian like this, using the reduced mass. We are working in the center of mass frame, so the center of mass term doesn't appear in the Hamiltonian. Okay, so this is our Hamiltonian, which I can write using the operator form of P, which is minus iota h cut del. So this becomes minus h square del square 2 mu, and sorry, this potential is negative because the charge of electron is negative E. So V of R is minus Z prime E square over R. So this is our Hamiltonian, and we have to find the eigenstate psi in the position space. And more precisely, we will work in spherical coordinate system, because it's a spherically symmetric potential and it would be a lot easier to work in spherical coordinate than in any other coordinate system. Okay, so let's write this Hamiltonian in spherical coordinate system. So in spherical coordinate system, our Hamiltonian is minus h cut square to mu and del square is 1 over r square partial by partial r square partial by partial r plus 1 over sine theta partial by partial theta sine theta partial theta plus 1 over sine square theta partial square by partial phi square minus z prime e square over r. However, we can immediately see that this thing plus this thing is nothing but the orbital momentum square operator. So I can immediately replace this with L square operator, and the reason is this, that we have already studied the eigenvalues and eigenfunctions of this operator L square. So this will make our life easy if we introduce an operator that we already know its functions of. Okay, so we have to find this state psi in spherical coordinate system. So in spherical coordinate system, our equation becomes r theta phi. If I project psi into spherical coordinate system, we get r theta phi psi. Now, since our solution, our operator, is sum of the terms like this and this, which is function of r, and then this term, which is function of theta and phi. Of course, there's a 1 over r square here, but we can take care of it by multiplying it to the other side. So we have essentially an operator which is sum of an operator which is function of theta phi, and sum of an operator which is function of r, which means that I can use method of separation of variable and assume that this wave function r theta phi can be written as a product of two functions. One is function of r and the other, let me arbitrarily choose some f of theta and phi. So I'm going to separate r and theta phi into two functions. Now let's substitute this here and this operator here, and we can get easily minus h square, h bar square, 2 mu r square, partial b partial r. Excuse me. R square partial b partial r minus L square over h bar square minus z prime e square over r, and all of this operating on f, and on the right side I have e f. Sorry, I made a mistake over here. This is equal to L square over h bar square, and with a negative sign, because L square operator is actually equal to minus h bar square into all of this. So all of this is equal to minus L square over h bar square. Okay, so this is the equation that we have, and let me rewrite it. So I can open the partial with partial r operator, and we get 2r partial with partial r plus r square partial with partial r square minus L square over h bar square rf minus z dash e square over r rf e r. So all I did is that I expanded this term, partial r partial this. So I applied the chain rule on this. So first I take its derivative, which is 2r, and this as it is, and then I kept this as it is and took its derivative, applied this here. So this is partial square over partial r square. Okay. So we notice one thing very easily. This is function of r, this is function of theta phi. So when this L square operates on both, and when all of this operates on both, I can see one thing, that these two doesn't affect f, so f gets out, and this 2r partial r plus r square, maybe I can put capital R here, r square partial square r. So this is here. So this term multiplies with this one, so I get plus. So when this L square operates on RF, R, it does nothing to R, so R gets out. So R L square F over 2 mu R square. This H bar square cancels with H bar square. And here it's like this, RF E R F. Now let's divide the whole equation by RF and multiply the whole equation by 2 mu R square. So what I'm going to do, multiply 2 out by 2 mu R square and divide by RF. So I'm going to do this operation on all of the equation. So when I apply here 2 mu R square, cancel with this 2 mu R square, and this RF, F cancels here and only R is left. So I have minus H bar square over R and 2R partial R by partial R plus R square partial square R partial R square. And over here I get L square F over F, because this is cancelled and R is cancelled and F is left here. So here I get 2 mu R Z dash E square is equal to 2 mu R square E, because this RF is gone, this RF is gone, and 2 mu E square, or 2 mu square R here, 2 mu square R here, one R is cancelled. Okay. Now let me just rearrange it a little bit. I can keep this thing on left side and take everything else to the other side. So this goes to the right side, H square over R, 2R partial R by partial R plus R square, partial square R partial R square. This goes to the other side, plus 2 mu R Z dash E square plus 2 mu r square e. Now if we look at this equation, on the left side, we can at most have something which is function of theta and phi. Because f is theta phi, this is theta phi, this is theta phi, and on the right side, everything is at most function of r. Now, if these two functions have to be equal, there's only one possibility in that they're both equal to a constant. Because if this is not equal to constant and then there is some r present here, then this thing cannot be equal to this because there is no r on this side. Similarly, if this is some function of theta and phi, this cannot be equal to this because there is no theta phi on right side. So only possibility is that this L square f over f is some constant, and whatever that constant is, this is also equal to the same constant. But if I rearrange this, I get L square f is equal to constant f. However, we immediately recognize that this is an eigenvalue equation for L square, and we have already the solution of this equation. We know that the constant is nothing but L into L plus 1, and this f is nothing but spherical harmonic that we have already found. So it means that L square YLN L into, sorry, this is h bar square here, h bar square y. Which means that this right side is now equal to L into L plus 1 h bar square, and I can actually do it a bit quickly, that put L into L plus 1 h bar square right in this place, and this equation now becomes, and I can multiply with this r f with this r everywhere because f is now gone. All of this is L into L plus 1 h bar square, and we immediately get minus h bar square to mu. Let me multiply with this 2 mu, and I can take, so I'm bringing this 2 mu r square to this side, so 2 mu comes here, and r square, let's take it inside, so when r square comes here, this r square goes away. So I have this term, and when r square comes here, this is nothing but 2 over r partial r by partial r plus L into L plus 1, and there's an h bar square divided by 2 mu r square. So where does the h bar square go? Did we make so this is mu, so there has to be an h bar square here, and minus, so this 2 mu r square goes away, and we have z dash e square over r is equal to e r, and this is our equation, differential equation that we can solve to find capital R. And once we do, we can now recognize one thing very quickly, that our psi that we begin is R y and m theta phi. Now this function, this psi, is actually an eigenfunction of three operators. It is an eigenfunction of Hamiltonian operator, because we started it like this, that this is an eigenfunction of Hamiltonian operator. But now we have additionally seen that its theta phi part is an eigenfunction of L square operator, and we already know that this YLM are eigenfunction of LZ operators as well. So it means that this whole function is an eigenfunction of Hamiltonian, L square, and LZ. And all three are commuting operators. So this is a simultaneous eigenfunction of these three commuting operators, which means I can also label the state psi now with energy L and M. So this is my state, which is now labeled by energy values L and M. This gives us the total angular momentum, this gives us the z component of angular momentum, and in 3D space we can label any wave function which is a function of the Hamiltonian, which is the eigenfunction of the Hamiltonian operator by ELM for spherically symmetric potentials. It's important that this is only valid for spherically symmetric potential, that is, that our potential is independent of theta and phi, because if this potential term had theta phi inside it, and which means there would be a theta phi here, we wouldn't be able to use the argument that we used here, that this and this, they both have to be equal to constant, because then it would have depended on what kind of theta phi dependence in potential is. So let me repeat that these eigenfunctions are eigenfunction of H, L square, LZ operator, but only for spherically symmetric potential, that is, the potential V of R is independent of theta and phi. It's only dependent on R. So this state is an eigenstate of these three commuting observables. Okay, so now our job is to find the solution of this radial equation and find these functions R, because once we have these R function, we can just substitute them here. We already know the spherical harmonic, and our knowledge of the eigenfunctions of Hamiltonian operator for hydrogen atom would be complete. And on the way, we will be able to find the energy eigenvalue. Okay, so let's now go to find the solution of this radial equation. Okay, and to find the solution of the radial equation, solution. So what we do that if we make this substitution, that we take R as some other function over R, this will go, this single derivative term go away, and our life would be a little bit easier, and we will get this equation minus h bar square over 2 mu, and I'm replacing partial derivative with total derivative, because our unknown is now only function of R minus this u of R e u of R. So we get a bit simpler equation for the radial function, but now we have an equation for u, and once we find u, we always have to remember that our radial function is actually u over R. Okay, now we need to solve this equation, and it would be easier if we reorganize this equation in a bit different way, because I can see this 2 mu over h cut square here, this 2 mu over h bar square here. So if we make a little change of variable, we can simplify the equation a little bit. And also, since we are studying bound solution of hydrogen atom, bound solution mean when the energy of the system is negative, that is the electron and the nucleus are bound together. So in that case, what happens, that energy is actually negative. So it means I can replace this E with minus some positive number, and if I bring it on this side, and also for later convenience, it would be easier if I divide by 4 throughout as well. That will make this equation look like this: minus d square by dr square, and this is 2 mu, and I'm dividing by 4 throughout, so this becomes 8 mu. Let me bring this h bar square here, and let's bring that energy E towards this side. So E is minus E, so this becomes plus, and this, let me put this E bar here. Similarly here I get L into L plus 1. Let's take this h bar square here, and I'm dividing by 4 throughout, so this becomes 8 mu, and that E is coming here, which is minus E, so this becomes negative, and E, this h bar square, let's bring it here, and we have this r square. Here I get z prime E square, so this becomes plus E bar into 4 r u of r, and on the right side I have 1 over 4 u of r. This division of by 4 makes our life easier later on. But now from here I can see that I can replace this part with some other variable, let's say rho square. This will also translate exactly the same way. This 8 mu E h square r square, this will become some rho square. But this I will have to work out over here, because I can make it rho, which would be the square root of this part. So if I do the transformation, so if we take some rho as 8 mu E mod h bar square square root into r, then the equation becomes d square r d rho square plus L into L plus 1 over rho square minus some lambda over rho into u equal 1 over 4 u, where this lambda is nothing but z prime e square over h bar mu over 2 epsilon this square. And the minus sign here, there's a plus here, so this becomes minus and this becomes plus. Okay, so all we did is just introduce a change of variable that made these terms simpler, but over here there were lot of other new constants that appeared here, so I grouped all of them into this constant lambda. And this is now the equation that we have to solve to find the radial functions R for the hydrogen-like atoms. So for that, let me shift to a new set of boards and we can begin it over there. Okay, so we have been able to transform our radial equation to this equation over rho square plus lambda rho into u1 over 4u. Sorry, I just want to point out that on the previous board, I mistakenly wrote capital R here, but that was actually u. And in fact, we don't even need u here because u is written all the way here. So that capital R written here is an error. Okay. Where this lambda was z prime e square over h bar mu over 2 magnitude of energy to this. Now this equation does not lend itself to a closed form analytical solution as it is. And we have to resort what is called a series solution method, in which we assume the solution to be in the form of an infinite series, and we plug the series here and then determine the unknown coefficients by matching left and right hand sides. Okay, but before we do that, we can actually make this equation a bit simpler if we recognize a couple of things. Number one, so two observations I can make. That when rho is very large, that rho goes to infinity, this equation is d square u by, because this goes to 0, this goes to 0 is equal to 1 over 4u. And this equation we can quickly solve it because this is a constant coefficient equation. So its characteristic equation is d square is equal to 1 over 4, which has roots d plus minus 1 over 2. It means that I can write solution u as some constant c1 minus rho by 2 plus rho by 2. So if we look at this solution, we see that since our rho, which is proportional to r, and r is nothing the distance of electron and the nucleus, which goes from 0 to infinity in general. So it means this rho is a positive number that goes from 0 to infinity. But in this solution, we see that this term will go to infinity as rho goes to infinity. So it means our solution for large r should only have a term like this. So for large r, our solution should have this term and this term shouldn't be there. So this is our one observation. The second observation I can make right by looking at the equation, that my u has to be such that when I take its double derivative and when I divide it by rho square, I should have the same function and with, let's say, L into L plus 1 with it. Since this lambda is a constant, so this with this term we can adjust, but with this term, with these terms, it has to be of this type. So our u should be something like rho power L plus 1. Because when it is rho power L plus 1, I take its two derivative, I will get L plus 1 into L, which is something like this. And after two derivative, I will have rho power L minus 1. And similarly, if this u is here and you divide by rho square, it is like rho power L minus 1. So with these two observations, we can guess that our solution is probably of this form, where this f of rho is still an arbitrary function. So we have to determine it, and even if our guess is not exactly right, that thing can be absorbed into this gas function f of rho. But let's substitute this gas solution into this equation, and we can easily show that after substitution and cancellation of various terms, we are left with an equation like this: d squared d rho squared plus 2l plus 2 rho minus 1 df by d rho plus lambda by rho minus m plus 1 over rho f is equal to 0. Okay, so this equation apparently is a bit more complicated than this one, but it turns out that this one is easier to solve than that one. Okay, now we have to find this function f, and to find this function f, let's assume that its solution can be written like this, that f is a power series like this, and our job is just to find this coefficient ck once we substitute this f into this equation. Alright, so let's do that. Let me substitute this thing here. So when I substitute here, I get k 0 to infinity and ck. The first derivative gives me k rho k minus 1. The second derivative gives me k minus 1, k minus 2 plus 2l plus 2 k 0 to infinity ck k rho k minus 1. We can note that when k is 0, this term is 0 because k is 0. When k is 1, this term is still 0 because this is k minus 1. And the summation really starts from k is equal to 2 to infinity, but let's keep it from k equal to 0 for generality. Similarly here, the sum actually starts from k is equal to 1 because for k is equal to 0, this is 0. And over here, so this is actually just minus this because this row is common to both. Sum over k 0 to infinity ck rho power k equal 0. Now in this equation, we can see that let's write it like this: k 0 to infinity ck k minus 1 k minus 2, and over here this multiplies with this and it becomes 2l plus 2 k 0 to infinity ck, and this row makes this row power k minus 2, and this is minus k 0 to infinity ck row power k minus 1, and this becomes lambda minus l minus 1 sum over k ck row power k minus 1 0. So we have row power k minus 1 here, row power k minus 1 over there. Here it's row power k minus 2 in both of these terms. So let's make this substitution, that we introduce another variable k prime, it is equal to k minus 1. And once we do that, our equation becomes k prime. So when k is 0, so as I said earlier, this k essentially starts from k is equal to 2, so we can still start it from k is equal to 0. K prime is equal to 0 because For k0 this term is 0 anyway. Similarly this term is k is equal to 0. For k0 this term is 0 because the sum actually starts from 1. So for k1 k prime is 0. Similarly, even though this one is 0 at k is equal to 1, but we can choose to start this from k is equal to 1. So this sum over k prime will be k prime from 0 to infinity. This is now c k prime. So if k prime is equal to k minus 1, then k is equal to k prime plus 1. So this becomes k prime plus 1. This k becomes k prime plus 1. This becomes k prime minus 1 plus 2l plus 2. So this is k prime is equal to 0 to infinity. This is c k prime plus 1. This k is k prime plus 1, k prime minus 1, and then these. So in both of these, let's keep k. We can make it k prime as well, but it doesn't matter. Lambda minus 1, k0 to infinity, c k minus 1 equal 0. Now what I can do that in the first two terms, since this k prime is just a dummy index for summation, I can make it whatever and everything still remains the same. So let me make this k prime is equal to k again, and we get the equation like this. So we write it here. So we get k0 to infinity ck plus 1, k plus 1, k plus 2l plus 2, ck plus 1. So all of this is common with k minus 1 plus actually minus k 0 to infinity ck. I think I missed a k here. So there was this k which came here. It should have been here as well. So k here. So this k becomes ck plus lambda minus l minus 1. Sorry, this is mixing up. So let me put a plus sign here. Then I can write minus k plus lambda minus l minus 1 ck rho power k minus 1 equal to 0. So all I did is combine these two terms and combine these two terms. So when I combine this, I got minus k plus lambda minus l minus 1 into ck and rho k minus 1 over here. Similarly for these two terms. Now this is a series which is summing to 0. So in general, this sum can be 0 only if all coefficients are 0, which means that ck plus 1, and in these two terms I get k into k plus 1 plus 2l plus 2 into k plus 1 plus, so over here the coefficient is ck minus k plus lambda minus l minus 1 equal 0. So this coefficient of this term rho power k minus 1 should be 0, which means that I can find ck plus 1 in terms of ck. Let me take all of this to the other side, so this becomes minus ck, and let me absorb that minus inside this term, so this becomes k plus l plus 1 minus lambda, and with this I have to divide it on this side, and while dividing let me take k plus 1 common between these two terms, so I get k plus 1 into k is left here and 2l plus 2 here. So this is the recurrent equation that can give us the coefficients for all of these terms. Okay, let me just see that everything is okay. And there is no error. Perfect. Okay. So just to give you an example, for example, for K0, we see that C1 is C0, K0, L plus 1 minus lambda, K0, K0, so I get 2L plus 2. Similarly, C2 would be when K is 1, so C1, so 1 plus 1, 2, plus L minus lambda, 1 plus 1 is 2, K plus 1 plus 2 is 3, 2L plus 3, and then C1 can be substituted from here. So if I substitute C1 here, I get C0 into whatever is left. So I can find all the coefficients just in terms of C0, which means that our final solution will have only one unknown, C0, which we can get from normalization. However, there's a trouble, and the trouble is, if you recall, we had the actual solution U like this: rho power n plus 1 e power minus rho by 2 f of rho. And our f of rho was assumed to be some Gauss series like this. Now if all of these coefficients are there, and we can see that these coefficients are something like 1 over k, because as you see from here, there's a k square down there, and there's a k over there, so all solutions are something like 1 over k, which means that if this series goes to infinity, this is nothing but a function like this, e power rho. And if this function is like e power rho, and I put e power rho here, then e power rho into this e power minus half rho is something e power plus rho by 2, and for rho infinity, this solution will go to infinity. So for the infinite series, we run the risk of going to infinity for this this radial function u, which means that our wave function would be infinite, which is against, which doesn't make sense, because we know that the wave function, the hydrogen atom is stable and everything is finite. So it means that we have to exclude this possibility of this series going to infinity, which means we have to find a way to restrict the series to a finite number of terms, which means that after a certain point, the number of coefficients, the coefficient should go to 0. That we might have like C0, C1, C2, C3, and then maybe C4, C5 all the way are 0. Or maybe we have coefficient 1, 2, 3, 4, 5, 6, and then after 6 all of them are 0. How do we make that happen? That can happen if and only if this lambda is an integer greater than or equal to 1. Because you see, all the coefficients are like this: L plus 1 minus lambda, 2L plus minus lambda, and then the next one would be 3 plus L minus lambda, and so on. If lambda is integer, for example, let's say lambda is 3. So when lambda is 3, we will put 3, and L is a number which can be 0, 1, 2, 3, 4, 5, etc. So if lambda is 3 and L is either 0 or 1 or 2 or whatever, so for a given L, if lambda is greater than L plus 1, at a certain point we will see that this term will get to 0. For example, L is 3 and lambda is 5. When L is 3, so this term would be 3 plus 1 minus 5 is minus 2. This is 2 plus, this was L was 3. So we were taking example that let's say L is 3 and lambda is 5. So if this is 3 plus 1 minus 5 is minus 1, then this is 2 plus 3, 5, minus 5, 0, and C2 is 0 and all other coefficients are 0. Suppose L is 3 and lambda is 10. So if lambda is 10, then this would be 4 minus 10, 5 minus 10, then next 6 minus 10, and at C is equal to 4 or 5, it would be 10 minus 10, and all the coefficients following would be 0. So it means that if lambda is an integer which is greater than L plus 1, it has to be greater than L plus 1, because if L is 3 and lambda is 2, this one will not be 0 and none of these after this will be 0. Because if this is 3 and this is 4, so 4 plus 1, 5 minus 3 is 2, then this would be 6 minus 3, the next one 7 minus 3, and we will keep on going without getting to 0. So even if L and lambda are equal, we will never get to a 0, because if lambda is 4 and this is 4, the first coefficient is 5 minus 4, which is fine. The next is 6 minus 4, then 7 minus 4, and so on. So lambda has to be an integer. So for finite series, we have this condition that lambda has to be integer and the integer has to be greater than or equal to L plus 1. Okay, so let me call that integer some n. Let lambda is that integer n, which is always greater than L plus 1. On the other hand, if I bring this one here, so L is always equal less than n minus 1. So if lambda is n, I can now quickly compute my energy as well, because lambda was z prime e square over h bar mu over 2. So this is equal to n. I can now quickly find this E mod. Let's take square on both sides, and I can take this there and this here. So by square z prime square p4 h bar square 2. This is mu. This n square comes square and e bar constant. This is the expression for energy, which exactly matches that of Bohr's model and experimental observations at the time of Schrodinger equation. By the way, if we put all of these values here, we get E mod 13.6 electron volt and square. And if you recall, E was negative of this, so energy is minus 13.6 electron volt and square. So we now have a description of our energy eigenstates, and that is that energy is equal to whatever this function over n square, and this n is an integer which is always greater than or equal to L plus 1, where this L is an index that represents the orbital angular momentum, so this energy is only dependent on n, though n has a condition, has a relation with L, that L is always going to be smaller than n, and both n and L are integers. Let me just remark one thing, that this expression for energy agrees very well with Bohr atomic model, but there is a difference. In Bohr's model, there was assumption that Each electron is in a shell or orbit around the nucleus with a definite angular momentum which was quantized, and even the n is equal to 1 state had an angular momentum. But we now know that for the n is equal to 0 state, which is the ground state of hydrogen atom, and which is possible because for L0 n is equal to 1, which is the first shell, but we know that for n is equal to 0, the orbital angular momentum is 0. Okay, so we have been able to solve this equation to find the value of energy, but we still have to find the wave functions using the solution of our function. Okay, so to find these functions, let me note one quick thing, that we had this choice, this transformation of variable when we transformed from r to rho, but we can express it in terms of another parameter, a naught and n. We put n here and r over a naught, where because there is an energy and I can replace the energy part with the corresponding n, and all the other things I can group into a naught except for 2z factor, where a naught is called Bohr radius, and it's a nice unit for describing distances at atomic scale, because this is roughly half an angstrom. Angstrom is 10 power minus 10. Okay, so we can describe our rho in terms of n and a naught. A naught is a length parameter, which is about half an angstrom, and n relates to the energy of the electron in that state. Okay, so let's now find the eigenfunction. Now, I don't want to make things complicated and write the general solution of u and f of rho because we're only interested in few basic examples. And if you, by the way, solve the radial equation that we was doing, f of rho is what is called Lagrange polynomials. It's polynomials because we have placed a condition on our lambda so that the coefficients become 0 after a while. So this f of rho is always a polynomial. Those polynomials are called Lagrange polynomials. So general solution is written in terms of Lagrange polynomials. But let's work out a couple of examples. Okay, so the first example is the most common one. This is the ground state. So for ground state, we have n equal to 1, which is the lowest value of n. And when n1, since L is always less than or equal to n minus 1, so there's only one possibility for L, that L is equal to 0. So when L0, n1, we see that C1, which was C naught, let me just see from here. So if this lambda is 0, this L is 0, and this lambda is 1, which is now n. So if this is 1, this is 0, 1 minus 1 is 0, so C1 is 0. So essentially, our C1 is 0, which means that my u of rho would be rho power L plus 1. L is 0, so it's just rho. And then there was exponential minus rho by 2. And then we have f. And in f, we only have C naught. So I only left C naught. There are no other terms. So this is my u of rho, where rho is given over here. And I can write it in terms of R like this. Some C naught 2ZR over A naught exponential minus Z R A naught for n is equal to 1. So n is 1. This is U of R, and we have to find this C naught, which we can do by normalization. And normalization is a little bit tricky. Because remember, we have to normalize this whole eigenfunction. Over all space in the universe. Okay? So this wave function, which I can write as R squared y square, and this dv in spherical coordinate system is R squared sine theta d theta d phi, and integrals. There is an integral over R from 0 to infinity. There is an integral over theta from 0 to pi. Then an integral over phi from 0 to 2 pi. However, we already know that these y square lm are normalized over the solid angle, over the complete sphere. So this integral over theta phi of yl square with sine theta, this is already 1, so we are left with this thing, that our normalized condition is integral from 0 to infinity R square. So by the way, if there's a modulus square here, but we don't need a modulus here because R is a real function anyway. So R square dr is equal to 1. So this is our normalization relation. However, since this capital R is nothing but U over R, if you recall, R was U over R. For U, the normalization condition is for U, it is 0 to infinity, U square dr is equal to 1. Okay, so you substitute this thing here, you find C naught, then C naught comes out to be Z over A naught square. So this is an easy integral to find out. You substitute this square here, the C naught 2Z A naught gets out of the integral, and you're left with R square exponential minus Z R over A naught. And two integrations by part will give you this value of C naught that we can use over here, and we will have our U function for the ground state of hydrogen. Okay, now I have to discuss a few other eigenfunctions, but for that let me shift to the next set of boards, and then we'll resume. Okay, so we just saw that U is equal to after finding C naught, U becomes 2Z over A naught 3 by 2 R exponential minus Z R over A naught, and now R 1 0 because n is 1, n is 0 of R is nothing but U by R, so this R goes away, and 2 Z over A naught 3 by 2 exponential minus Z R over A naught. So this is our radial function for n1 L0. Similarly, we can find the coefficients C1 for R2 0, for n to L0 and normalize our radial function to get radial function like this. And as you can expect, that this now tells us that this is a polynomial of order 1. So C0 and C1 turned out to be non-zero for this case because n was equal to 2. So we could go to C1, and C2 and C3 all were 0. So we have a polynomial with 2 terms from f of rho. So that gave us this function. Similarly for R to 1, now L is 1, so we will have one less coefficient than for L0, and if we normalize the function in a similar way, we get ZR over A0, only one term in the polynomial, exponential minus ZR over 2A0, and similarly you can find other in the books as well. However, I just want to remind you that our complete eigenfunction is, it's actually sometimes written as NLM of R theta phi, to remind us that there are 3 indexes that label this state: N energy, L angular momentum, M the z component of angular momentum. And this state is a simultaneous eigenfunction of Hamiltonian, L square and Lz operators. And since this depends on N and L, we can write it like this, and there is a momentum eigenfunction part YLM. So this is our total eigenfunction for the hydrogen-like atoms. There's one peculiar feature of these eigenfunctions, which is that energy only depends on index n, and it doesn't depend on L and M. So it means for each n, whatever the value of L and M is, the energy is the same when the atom is alone. That is, there's no external perturbation or external force acting on it. So an independent, or you can say an atom on which nothing else is influencing, and we only consider the equilibric interaction of electron and nucleus by neglecting spin and everything else, our energy is only a function of n. This is what we call degeneracy, and all those states that are different because their L and M are different. For example, this is a different function than this one, but for both of them, energy is the same because n is equal to 2. So we call them degenerate states because all of them degenerate to a single value of energy. And let's work out the degeneracy of these solutions, and we see that for each value of n, there are n values of L, because L goes from 0, 1, 2 up to n minus 1. So these are n values. If n is 3, this is 2, so 1, 2, 3 values. If n is 4, this goes until 3, so 1, 2, 3, 4 values. So for each n, there are n values of L, but for each L, there are 2L plus 1 values for M. Because, for example, if L is equal to 3, M goes from minus 3, minus 2, minus 1, 0, 1, 2, 3. So these are 1, 2, 3, 4, 5, 6, 7. And 2L plus 1 is 2 into 3 plus 7. So for each L, there are 2L plus 1 values. And if I want to compute in general the number of states for each n. We see that we have to sum over L from 0 to n minus 1, and for each L there are 2L plus 1 states, and if you perform this sum you get n squared. So it means that in hydrogen atom each energy level is n squared degenerate, that for n is equal to 1 there is 1 state, for n is equal to 2 there are 4 states, for n is equal to 3 there are 9 states, and so on. Remember, we are not taking into account the spin of the electron, that we will see that increase the degeneracy by twofold because each electron can have either of the two spins which give rise to 2 states for each value of n. So, but neglecting spin, the degeneracy of solution of Schrodinger equation is n squared for hydrogen atom. Okay, so let me now get back to another important concept. And suppose, and actually want to discuss how to visualize these functions. We have, nucleus at the center, and then the electron could be somewhere here, and we have been able to find solutions that are function of r, theta, and phi. So for y and m, we have already seen that, for example, for L0, it's a spherically symmetric solution, s orbital. For L1, there were 3 possibilities for 3 values of m, and we can find linear combination to have 3 orbitals, one along z-axis, one along x-axis, one along y-axis, and so on. But right now, neglecting that and focusing on r, let's see how do we interpret this radial function r. To do that, suppose we want to answer this question: what is the probability of finding electron around the nucleus from somewhere r is equal to a to r is equal to b? So I'm asking this question, that suppose I want to see that there is this region around the nucleus with inner radius a and outer radius b, and I want to see what is the probability of finding the electron in this shell of thickness b minus a around the nucleus. To do that, I not only have to focus on this, but always have to remember that my wave function is all of this. So, and this region has full range of theta and full range of phi. So it means this probability would be psi square volume element, and my integration over r would be ra to rb, integration over theta would be theta 0 to pi, and integration over phi would be 0 to 2 pi. Of course, if you're interested only in finding probability in this region, all you do is restrict your angular range as well. But right now, I'm interested in finding the probability of particle from A to B in all of this spherical region. So my theta and phi are integrating from 0 to the full range. Now, this phi square, so this is my probability that I'm interested, is nothing but r square and into ylm mod square. You don't need mod here, you can put if you want, because this is not a complex function. And this, the volume element is r square sine theta d theta d phi dr integration over r theta phi. And this I can write, I can separate actually into two parts. Integration over r from a to b is r square, small r square, dr. Integration over theta and phi from 0 to full range is y lm mod square sine theta d theta d phi. But these YLMs are already normalized over the full solid angle range. So this integrates to unity, and I'm left with probability of finding particle from R is equal to A to B by A to B R square R dr. So you see, the radial probability is not just probability density is not R square. So let me just say probability density is R square, and not just R square, because we cannot forget this YLM part, and also to remember that we have to integrate over theta and phi. But fortunately, all of that can already be taken care of by the normalized YLM. So this R square, which is coming from the spherical coordinates volume element, because volume element is R square sine theta d phi dr. So this R square has to come here. So if we want to interpret this integral, we can interpret this as a probability density, because this dr is just integrating this probability density. So wave function is R, but probability density is not R square, but R square. And that's an important distinction that we have to keep in mind. For example, if I, let's say, plot the radial function and the radial probability density, I should get something like this. So my R10 function is, so let me actually bring this board down and plot them here, because we have these functions written here already. So let me plot this radial function and the radial probability density corresponding to that radial function. For example, this R10, this is just a constant. So this is an exponentially decaying part. So its plot is something like this. However, if I multiply R square and take its square, if I take its square, it still remains exponentially decreasing, because I will simply get a 2 here. But an R square here would mean that, so let me label this is R10. And now if I multiply this R with R square, I have a function like this. So R square, R10 square is something like R square exponential minus 2 ZR over A0. So this function at R is equal to 0 is 0, whereas this was non-zero. So that's why at R is equal to 0, it started at somewhere and then came down. But this one at R is equal to 0 is 0, and when R increases, this initially increases, and then after a while, when R is very large, this takes over and it starts decaying again. So its plot is something like this, and it actually peaks at R is equal to A0. So that's why in this n is equal to 1 state, electron is most likely to be found at a radial distance of about 1 A0 from the nucleus. So because there is a peak probability density from the nucleus. So nucleus is located at R is equal to 0, and this is the radial distance from the nucleus. So even though the radial function is peaking at the nucleus, but the probability density is peaking away from the nucleus. Similarly, this R20 function if we plot it, this is something like this. It actually at r is equal to 0 is non-zero, because r0, this is non-zero, this is 0, but there's a 1 here. So 1 into non-zero term is something non-zero. And when r increases, initially this term takes over quickly, so we go to the negative region, but after a while when r is very large, so when r is large, you can forget this 1, so that's why for r large the radial function is negative, but then this keeps on decreasing its value and eventually it reaches 0. And if I plot its r square into this function, it's something like this. So it's peaking somewhere around 5 times a naught. And we can see that this tells us that the probability of finding the particle in n is equal to 2 and L is equal to 0 state is maximum somewhere in this region. However, important thing is to remember that it's non-zero over quite a large range. So even an n is equal to 2 electron can be found, even though with a very small probability, even at a similar, in a similar region where n is equal to 1 electron is being found. And similarly, there's an overlap with this function as well. For r is equal, for r to 1 state, if we draw its plot, it's something like this, and its r square part is also something like this. So this is r2 1 square, r square, this is r2. So you see, for L is equal to 1 state, the probability of finding the electron is maximum in a region which is actually nearer to the nucleus than the L is equal to 0 state. Perhaps that's the reason that the first electron would like to fill this L is equal to 0 state than L is equal to 1 state. So these radial function actually tells us the radial spread of the wave function and the probability density of the electron around the nucleus. However, we have to remember that to find the total probability around the nucleus, we have to keep in mind that there is an angular part, YLM. So the total probability density is the square, is proportional to the square of all of this function. Okay, so with this we can end our discussion of the hydrogen atom. We found that the solution of Schrodinger equation for a hydrogen-like atom, where the potential is central potential, they are actually simultaneous eigenfunctions of orbital angular momentum square operator and the z-component of angular momentum operator and the Hamiltonian operator. These eigenfunctions are actually very important when we will be building solutions for multi-electron atoms and when we want to understand the effect of other external fields, because to build those solutions using perturbation theories, we need this solution as a sort of a fundamental basis in which we can express our eigenfunctions of more complicated states. Thank you.